In this lecture, we discussed the numerical solution of initial value problems. We started the discussion with defining what initial value problem is, namely an ordinary differential equation, equipped with also an initial condition such that the solution to this ordinary differential equation is uniquely defined. We argued that the exact solution to this ordinary differential equation or initial value problem is not a number or a value, but it's rather a function y of x, and that we approximate this function using numerical methods on specific points x1, i1 to xn, yn. We discussed several numerical single-step methods, where each of these can be written as follows, that we sequentially update the numerical solution y at step I plus 1 as an update to the previous step, yi, plus a width h multiplied with a slope. And we saw different kinds of methods, explicit Euler, implicit Euler, modified Euler, midpoint, where each of these methods have a unique definition for how we use and how we define this slope. We generalized the discussion that before that only went about first order single ordinary differential equations to also systems of ODEs, and argued that, well, very minor modifications are necessary in order to solve systems of ODEs compared to single ODEs. Also, in an optional video, I discussed how this can be related to higher order initial value problems, where they can be easily transformed into a system of first order initial value problems. And then you can simply use the methods that you've learned beforehand. We also discussed the concepts of stability. So stability where there was a limitation on the step size h that could be chosen in order to obtain a stable and well-behaved numerical solution to an otherwise stable initial value problem. We also discussed the concept of stiffness. Now, stiffness means that, well, there are various components with varying rates of speed, let's say, in your solution. So very fast components that require you to take very small steps h, but also slow components that require you to integrate over a long horizon. And the combination of these two, well, they rendered us to the conclusion that explicit methods are very poor in such systems, and that implicit methods, which are much less prone to such stability conditions, are the method of choice here. We closed off the discussion by discussing the ODE solvers that are available in MATLAB, and then mainly the ODE 4.5 integrator. So that wraps up the video lectures for 2WN50. I hope you learned something from these lectures and that you enjoyed watching them. I hope to see you in the closing lecture, where we discuss some further questions that you may have, but also we will go through some exam questions from previous years, and I will try to work through them such that you have an idea of what is expected from you in the final exam.